Hello, in this video we look at the exponential family of distributions and specifically the log normal distribution within that family. And this is a follow-up video that we did calculating the mean and the variance of a general exponential family distribution. And we're going to show that it works for the specific distributions within the exponential family. We also showed that if you can write the density in terms of something like this, then it's considered the exponential family. Now this second one is called the canonical form of the distribution, and the beauty of this is that this log partition, the a of a function of our vector eta, is the derivatives end up being the moments of our sufficient statistic t of x. So let's show first that the distribution can be written in exponential form, and then find the mean and the variance of the sufficient statistics. So this is a density for a log normal distribution, and next we want to put it in this form. So we have to think about a function of the data, function of the parameters times a function of the data, and then a function of the parameters by themselves. So here this x and the square root of 2 pi can be offset, and that is going to act as our h of x. And so this here, we take the log and then exponentiate it, and we get this. Now over here we expand this quadratic into this, and it's all, of course, the minus and divided by 2 sigma squared. Now, since this is a e to an exponent, we can just add the exponents. So this comes straight down, and what we do is we're going to look at each case individually. So let's look at this one. So the 2's cancel. Of course, the minus makes that a plus. So we have mu over sigma squared times the log of x. And this one here, we just have minus 1 over 2 sigma times log of x quantity squared. Then we have minus log of sigma. And here we have mu squared minus 2 sigma squared. Now this is in, well, it's in exponential form, but let's write it in sort of vector notation. So these two terms can be written in this vector product, where this comes down, this is minus 2 sigma squared, and then it's log of x times log of x squared. You know, the x comes down, and this log partition, we need it minus something to put it in this form here. So we write it like this. Now, so it is in the exponential family. So, but to put it in canonical form, we reparameterize this and we just call this eta 1 and eta 2. And then we write the log partition in terms of eta 1 and eta 2. So that's what we do here. If we just generically call this eta 1 and eta 2, then the log partition becomes this. Now, if we were to plug in what we know about eta 1 and eta 2 into here, we would get this log partition back, and we should, because these are the same, just reparameterized differently. But the beauty of parameterizing it in canonical form is that we get to take partials of this log partition, and it ends up being the moments of our sufficient statistics. So let's look at that. So the mean of our first sufficient statistic, which is log of x, that is the partial of our log partition with respect to eta 1. Now our log partition was this, so we take the partial of it with respect to eta 1. Now there's no eta 1 here, so that drops out, and there's an eta 1 here, so it's going to be 2, eta 1, and so it ends up being this. Now we plug back in what we know about eta 1 and eta 2, which are these, and then we simplify it, and it is equal to mu. So now the mean of our second sufficient statistic is going to be the mean of the log of x quantity squared, and that says it's the partial of our log partition with respect to a to 2. So now this is our log partition, and so we take the derivative with respect to a to 2. That piece is this, and then the minus 1/2, and then the derivative of that log is 1 over, and then the derivative of the component we get minus 2. So this is it. Now we simplify it by plugging in what we know about a to 1 and a to 2, and we get this. And then when you simplify that, you get mu squared plus sigma squared. Now the variance of our first sufficient statistic, so it's the variance of the log of x, that's the second partial derivative with respect to a to 1 of our log partition. Now we already took the derivative once with respect to a to 1 right here. So let's just plug it in and then take the derivative again, and we get this. Then we plug in what we know about a to 2, which is this, simplify, and we get sigma squared. Now let's find the variance of our second sufficient statistic. So it's the variance of log of x quantity squared, which means it's the second partial derivative of our log partition with respect to a to 2. Now we already took the derivative with respect to a to 2 once, and we got this. So we'll plug it in here. Now let's take the derivative again of this, and we get this function. Now we plug in what we know about a to 1 and a to 2, simplify, and we get 4 mu squared sigma squared plus 2 sigma to the 4th. Now the covariance between our sufficient statistics, so the covariance between the log of x and the log of x squared, it's the log of x quantity squared, so this whole thing squared, that's the partial of our log partition with respect to a to 2 and then a to 1. So now we've already taken the partial of our log partition with the a to 2 once, and we got this. No, that was a to 1. This. So we plug it in here. Now we take the partial with respect to a to 1. Well, this is constant, drops out, and then this we get here, and we plug in what we know for a to 1 and a to 2, and then this simplifies to 2 mu sigma squared. Now, and that's all I have for today. One note is to go back and look at what we got for the univariate normal distribution when we've looked at the moments and covariances, and you'll notice that it's 100% the same. Anyway, that's all I have for today. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.